All motorcycles have a suspension system. But how do they work? Why are there different settings for different applications? And how do you set it up? Let's figure this stuff out. The goals for any motorcycle suspension system are the following. We want maximum traction, traction feel, controlled pitch, minimal harshness, controlled bottoming, and consistency. So for starters, what is this so-called maximum traction? This all starts with the tires. Rubber generates friction in three major ways: adhesion, deformation, and wear. Let's start with adhesion. Adhesion is a property of rubber that causes it to stick to other materials, like tape. If the two surfaces were perfectly smooth, the true area of contact would be the same as the observed area of contact. But this is not the case. Real surfaces are actually very rough, so contact is limited to the highest protuberances on each of the two surfaces. So as you can see, larger loads on the rubber presses the road irregularities into the rubber, increasing the contact area. More area in contact means more adhesion between the surfaces and higher friction forces. Deformation, or mechanical keying. When rubber is in contact with a rough surface, deformation comes into play. Movement of a rubber slider on a rough surface results in the deformation of the rubber by high points on the surface called irregularities or asperities. A load on the rubber slider causes the asperities to penetrate the rubber, and the rubber drapes over the asperities. The energy needed to move the asperities in the rubber comes from the differential pressure across the asperities as shown. Wear. In addition to the adhesive friction and deformation friction, rubber produces traction forces by means of tearing and wear. As deformation forces and sliding speeds go up, local stress can exceed the tensile strength of the rubber, especially at an increase in local stress near the point of a sharp irregularity. Tearing absorbs energy, resulting in additional friction forces in the contact surface. Now we can write a more general equation for rubber friction. The maximum lateral force that can be developed increases as the vertical load increases, as shown in segment 1. But because of tire load sensitivity, it is at a diminishing rate. So for a pneumatic tire, the coefficient of friction decreases as the vertical load increases. So in order for the tire of a motorcycle to provide maximum traction, they should be in contact with the ground, not bounce or oscillate, be loaded up appropriately. But what does suspension have to do with this? Let's have a look at a motorcycle without any type of suspension except its tires. Our inappropriately designed bike goes over a simple bump, and what happens? The front and rear tires lose contact with the ground at the back of the bump because the tires do not have enough travel to soak up the bump. When the tires regain contact with the ground, the motorcycle oscillates, bouncing up and down. So in other words, the bike will lose traction over bumps, have an uncontrolled pitch because of the unwanted oscillation going over bumps, be very harsh. Let's try to fix this situation by introducing a spring between the motorcycle and the wheels. We now have what is called a sprung mass, which is the mass above the spring, and unsprung mass, which is the wheel and other components going up and down together with the wheel, such as the brake discs and calipers. Ideally, we want the load between the tire and ground to remain constant going over the bump. We also want the sprung mass to move in a straight line. So, what happens if we ride this motorcycle with only a spring between the wheel and the sprung mass over the same bump as before? It does better than the bike without any suspension. The amount of time in the air at the back of the bump is lessened and the ride looks slightly smoother. However, we still see oscillation after the bump, causing loss of traction. So how do we fix this? Let's add a damper between the sprung and unsprung mass as well. The sprung mass follows an almost horizontal line, and the unsprung mass is in contact with the ground throughout the scenario, except for a very small bit at the back of the bump. We can also see that the bike does not oscillate after having hit the bump. So, this is a simplified version of how the suspension works on most motorcycles. If you want to see more content like this, please subscribe to my channel. Also remember to hit the bell notification button so that you know when I'm posting videos. If you're on Instagram, my page is called Mike on Bikes Official. There I post videos fairly frequently of when I'm out and about. Okay, so we understand the fundamentals of tire traction and of a spring and damper suspension system. Now we need to understand some basic motorcycle geometry. You may have noticed some fundamental flaws with the simplified motorcycle design shown earlier. Namely that the front end doesn't have any rake angle, which means that this motorcycle would be extremely unstable. So unstable that it would be hard to ride it even at bicycle speeds. So the rake angle is the angle between the steering axis with respect to a vertical line. The wheel plus tire has a certain diameter, and from these measures we derive a very important measure called trail. Trail is a measurement of how far the contact patch of the front tire is behind the point where the steering axis hits the ground. So why is trail so important? Well, trail is what makes it possible to stay balanced on two wheels, because it forces the front end to stay straight when a motorcycle is driven forward. So the further the wheel is behind the steering axis, the more stable the bike is, and vice versa. So less trail equals quicker steering bike, but also more unstable bike. The effect is obvious if you have seen a motorcycle going down the track in a straight line when the riders fell off. The bike wants to go in a straight line because of trail. The amount of trail you have can be adjusted by changing the triple clamp offset. Longer offset equals more trail and vice versa. Moving the fork tubes in the triple clamps, moving them upwards will result in less trail and vice versa. Changing the front wheel diameter. A larger wheel will provide more trail and vice versa. Adjusting the fork bottoms to move the axle back or forward. Moving the axle forward will result in more trail and vice versa. Lastly, you can adjust the ride height in the rear. Lowering it will increase the rake, which provides more trail. Okay, cool, let's add some rake to our motorcycle, and also some brakes. I mean, it would be good to be able to brake before the corners, right? Now, what will happen if we apply the front brake with our front fork at an angle like this? Well, first of all, the front forks will compress. This causes the wheelbase to decrease, simply because the forks are moving at an angle. So the wheelbase is the distance between the front and rear axles. A bike with a short wheelbase will transition side to side and turning quickly, but has the downside of being unstable. A bike with a long wheelbase will transition slowly but will be more stable. So, braking with an upside down or conventional fork will have the effect of decreasing the wheelbase of the bike, making it unstable but easier to steer. Secondly, as the fork compresses, they run out of travel, and thus their ability to travel over bumps decrease as the fork tubes bind and static friction takes over. This effect is called brake dive, and is a very important attribute that one must consider when designing a suspension system. Some older viewers might be thinking to themselves, wait a minute now, didn't engineers solve this problem with brake dive a really long time ago? Like with, for instance, the Earl's fork, or later the Saxton Moto D, the Hossack fork. So the Earl's fork is a variety of what is called a leading link fork, which suspends the wheel on one or several links with a pivot point aft of the wheel axle. When the front brakes are applied on a motorcycle with this type of a fork, the suspension extends, providing more travel. Another feature with this front end is that the wheelbase is not changed much at all, even with a lot of travel. So what are the downsides with the Earl's fork then? Let's think back to the goals with an ultimate suspension system. We want maximum traction, traction feel, controlled pitch, minimal harshness, controlled bottoming, and consistency. While Earl's forks are theoretically good at almost everything, they lack traction feel. First of all, having the front end rise when braking is counterintuitive. So it is something that a rider would have to spend a long time getting used to. Secondly, with added pivot points comes added play in the system. This removes feel of the front wheel traction. Think about it. Which motorcycles provide the best feel for front wheel traction? Sport bikes with clip-ons. The clip-ons are mounted directly to the forks and the rider leans over the front end. So, while you theoretically speaking could brake harder with an Earl's fork because the fork provides more travel, the rider wouldn't have much feel for the front wheel traction, which is of course very important when being on the brakes going into a turn. Okay, so what about the Saxton Moto D, aka the telelever, or the Hozak, aka the dual lever forks? They suffer from similar shortcomings as the Earl's does. And it is the same with hub center steering. So have there ever been any race-winning bikes with a front end other than telescopic forks? Well, of course. The 1990s Britain V1000, designed and built from first principles by John Britton and his team in New Zealand, had a Hozak front end. They were successful at the Isle of Man, Daytona, winning the Battle of the Twins in 1994. Another example of successful bikes with leading link forks is this 125cc Honda factory motocrosser from 1980, which was originally designed by Valentino Ribbi. Yasuto Fukuji won the 1981 All-Japan 125 Motocross Championship with that bike. So, did all other manufacturers all of a sudden adopt that front end after that? Nope. For now, telescopic forks still provide the best balance of tunability, traction feel, mass, and simplicity for most consumer motorcycles and race bikes. If you want a more in-depth explanation of everything that I'm talking about in this video, here are some great books to get you started. So we talked about braking, now what about accelerating? Well, if we're going to talk about accelerating, we need to understand the rear end a bit better. Let's look back at the simplified motorcycle design shown earlier. Let's assume it has a chain drive. When you roll the throttle, our simplified motorcycle will squat or pitch rearward. What does this do to our suspension travel? It diminishes our travel. To solve this problem, we need to introduce anti-squat, or in other words, we need to stop the rear suspension from compressing under acceleration. On a motorcycle with a chain, there are two primary ways to achieve anti-squat. One is to put the swing arm at an angle. Look at where the swing arm is connected. This is called the swing arm pivot point. Now look at the rear axle. Draw a line through the pivot point and the rear axle. Then imagine a horizontal plane that goes through the pivot point. The angle between the plane and the line is the swing arm angle. Imagine what happens if the rear wheel is driving the bike forward. Because of the upwards angle of the swing arm, the suspension is extended. The second force enabling anti-squat comes from the chain pulling on the axle in a direction parallel to the top chain run, which will extend the rear suspension. The amount of anti-squat you gain from chain pull can be altered with sprocket sizes. So now you might be asking yourself, how much anti-squat do you actually want? The so-called amount of anti-squat is easiest explained as a percentage that indicates how much weight transfer is offset by anti-squat. If you have, for instance, 60% anti-squat, its effect offsets 60% of the weight transfer on acceleration, and thus the suspension would still compress. At 100% anti-squat, the suspension would not move due to weight transfer. How much you want depends on a lot of factors, and the books I mentioned previously all provide slightly different answers. At the end of the day, the answer for road racing machines lies around 100% at corner exit. Important to note that corner exit isn't some neutral state, but rather a real-world case where the throttle will be applied and maximum grip on the front and rear wheel is desired. We must remember that the rear wheel moves in an arc when the suspension compresses and extends. This alters the swing arm angle and thus the force is generated. If the rear end squats too much, you will lose traction on the front tire because of load transfer, causing the bike to understeer. If you are experiencing this on your motorcycle, you need more anti-squat. If you have too much anti-squat, the center of gravity will move upwards, which will pull the tire away from the ground, resulting in loss of traction, or in other words, the bike will oversteer dramatically. I think you get the gist of it. It all depends on the bike, the rider, the track, and the conditions. The books I recommended earlier provide methods to measure the anti-squat percentage with the bike in a neutral state using various methods. If you want to adjust anti-squat, you can do this by changing sprocket sizes front-rear, which changes the chain pull. A smaller front sprocket will provide more anti-squat, and a larger rear will provide some but not as much anti-squat effect, and vice versa. Adjusting the ride height on the rear suspension, which changes the swing arm angle. Taller ride height equals more anti-squat and vice versa. Shortening the swing arm length by moving the rear wheel and shortening the chain, which will provide less anti-squat and vice versa. Moving the swing arm pivot point, which is not possible on most consumer available bikes. Moving the front forks and the triple clamps, which changes the swing arm angle as well as the trail. Moving the fork tubes up will decrease anti-squat and vice versa. What about the way that the shock attaches to the swing arm? This is very important indeed. Most modern motorcycles utilize what is called a rocker arm and linkage suspension with a single shock. This enables progressively stiffer resistance to wheel deflection using a constant rate spring, which combines sensitivity to small bumps with an increase in check for larger ones. All the manufacturers have a slightly different name for their specific systems, but they all work in basically the same way. There's not really a substitute to linkage rear suspension for racing. There are some rare cases that can be made for hard enduro bikes where mass is very important and the speeds are low. There, a simple swing arm can be used with progressive springs. What about how to distribute the weight on the motorcycle's front and rear, also called weight bias? Most sport bikes are set up to provide 50-50 weight bias including the rider, but remember, the rider's weight will affect this. Dirt bikes usually have a weight bias towards the rear, 45-55 with a standing rider, which again is affected by the rider's weight and position. Dirt bikes allow the rider to move around significantly and thus the weight bias can be shifted easily. On sport bikes, the weight bias can be altered by moving the rear wheel fore aft. Moving the wheel rearward will result in more weight on the front wheel. Padding under the saddle can also help move the rider forward on the bike. So now that we understand basic tire traction, motorcycle geometry, and the front and rear ends of motorcycles, it's time to tackle springs and dampers. As we talked about earlier, both your front and rear suspension have springs, which have a certain spring rate. The spring rate is the stiffness of the spring, commonly measured in newtons per millimeter or pounds per inch. These springs are set up from the factory with a certain amount of preload, which means that the spring is compressed a small amount from its free length. The spring rate and preload also affect something very important, and that is the ride height as well as the suspension sag. Now you already know that the ride height has an effect on the motorcycle's geometry, which will alter the turn-in as well as acceleration phases of cornering. Suspension sag refers to how much the motorcycle's suspension compresses from fully extended with the rider on board. This compression is very important because it enables the suspension to extend down into dips and depressions in the road surface. Without suspension sag, the tire would lose traction going over these dips. The spring rate which you need will vary depending on your weight and the application. An easy way to check if you have the right spring rate for your motorcycle is to measure your suspension sag and see if you can adjust it to the range given by the owner's manual. If there is too much sag in the suspension and you run out of preload adjustment range, you need a stiffer spring. So there are primarily two types of springs: straight rate and progressive. Straight rate springs maintain a constant rate throughout its travel. Progressive springs change their rate in relation to where they are in their travel. There are many variations of progressive springs, with true progressive, dual rate, triple rate, and so forth. Which type of spring you need will depend on the application and personal preference. According to Racetech's Motorcycle Suspension Bible, straight rate will be the best option for most bikes and applications. Progressive springs have the advantage of providing controlled bottoming, which we talked about at the very beginning of the video. However, with a modern linkage rear end, bottoming out is not a big issue. We should also remember that telescopic forks contain airspace. As the fork is compressed, the space gets smaller and the pressure increases. This affects the total spring force of the forks in a progressive manner. Also, adding more oil in the fork tube will decrease the airspace and thus affect the total spring force. I mentioned that you should measure your suspension sag. Well, how do you actually do this? Well, there are several methods, which you can read about in the books that I mentioned. For the rear suspension, you need to measure the distance between the axle and a near vertical point on the frame with the suspension fully extended, and then with the rider sitting on the bike. To fully extend the rear suspension, you need to get the rear wheel in the air. With dirt bikes, you can lift them on top of a stand. With a touring bike, you can get them on a center stand. Please see your owner's manual on how to do this on your specific motorcycle. So for the front suspension, you need to do this. Put a zip tie around the lower fork legs. Put the bike in a shock or have someone hold the bike steady while you sit on it. Push the bike down slightly and let it settle. Have your mate push the zip tie to the dust seal. Now get off the bike and pull the bike up so that the front suspension fully extends. Have your mate measure the distance between the zip tie and dust seal. That is your sag. On most motorcycles, you adjust the front fork preload with a wrench. They typically move independently of the fork tube, looking like this. More lines equals less preload. Fewer lines equals more preload. Please see your owner's manual on how to do this on your specific motorcycle. Lifting the bike up and letting it back down and pushing it down and letting it back up is a great way to check the health of your suspension system by checking what is called the stiction zone. So the stiction zone is the difference between where the bike stops when being pushed down, let back up, and lifted up and being let back down. Suspension Bible recommends having a stiction zone of 20 to 40 mm for telescopic forks and no more than 6 mm for the rear suspension. If the stiction zone is bigger than that, your suspension system needs a service. Now let's talk about damping. What is damping really? Well, damping slows down the movement of the suspension. Compression damping slows down the suspension as it compresses when going over bumps. Rebound damping slows down how fast the suspension extends. I'm not kidding, it's that simple. Damping in modern suspension components almost always involve a fluid that is forced through a hole or in more complex system a bending shim stack. The degree of damping is mostly determined by flow rate. When you adjust the compression and rebound on your suspension, what you're really doing is adjusting the flow rate. The flow rate is also affected by the oil viscosity, which is a measure of a fluid's resistance to flow. A more viscous oil is more resistant to flow. So compression damping slows down the suspension when going over bumps. The velocity of the compression is affected by the size, shape, and speed at which you hit the bumps. Bumps with a slope causes slow suspension movement, while bumps with a sharper edge causes fast movement. Thus the need for high-speed and low-speed compression damping. Compression damping affects the traction feel, plushness, and bottoming resistance. So it's easy to understand that if you add more compression damping, you get more bottoming resistance. It is also easy to understand that more compression damping provides less plushness and thus causes a jarring ride. But what about traction and traction feel? Well, actual traction is not that complicated. Going over a bump will cause the wheel to lose traction because they lift above the crest and thus the tires are unloaded. If you have too much compression damping, going over a bump will push the whole bike or sprung mass upwards, creating a harsh, jarring ride. So where do you adjust the compression? On most bikes with upside-down forks, you adjust the compression damping on the bottom of the forks. This can be counting turns from a mark or clicker style where you count the clicks. On the rear shock, the compression adjustment is usually located on top of the shock. Most of them have an indicator of plus-minus as well as a short text saying comp. Please see your owner's manual on how to do this on your specific motorcycle. So how do you know what compression damping you need? Well, the suspension should not bottom. You can check this by putting a zip tie around the lower fork leg on an upside-down fork. If the zip tie is pushed all the way down, you're bottoming out and probably need more compression damping. If compression damping isn't solving the problem, you need stiffer springs. You also want a plush ride, which is usually achieved by less compression damping. Maximum traction is found somewhere between the forks not bottoming out and a really plush ride. Now what about rebound damping? So rebound damping slows down how fast the suspension extends. Less rebound damping means the suspension extends faster. and more means it extends slower. When going over a bump, not enough rebound damping will cause the suspension to extend rapidly over the backside, causing the tire to oscillate. Too much rebound damping diminishes the available suspension travel by packing, which can happen over a series of bumps, where the suspension does not return to its original starting point, with each bump reducing the available travel. Less rebound damping generally provides a more plush ride, and adding rebound makes the ride more harsh. Testing rebound damping requires practice and a lot of testing. One way is to do the so-called push test. This is where you stand next to the motorcycle and push down hard on the saddle. You then let your hand rest on the saddle as the suspension rebounds up. You're observing how fast the suspension extends and if it bounces on the top. If you have too much rebound, the suspension will extend slowly and settle on the top with no bouncing. If you don't have enough rebound, the suspension will extend rapidly and bounce several times on the top. Front fork rebound is usually adjusted on the forecap, and the rear shock rebound is usually located on the bottom of the shock. Please see your owner's manual on how to do this on your specific motorcycle. I hope you've learned something from this video and that this has sparked an interest in you for motorcycle suspension and dynamics. Get one of these books and get learning.
It's gotta be against the law to look this damn good. Watch out now. Cause baby, I feel real good and I wish I would. Watch out now. It's gotta be against the law to look this damn good. Watch out now. Everybody watch out. Watch out now. I'm ready for a good time and I came to groove. The whole band's here and we came to move. Got a fresh haircut and 2 new shoes. We're here all night like we got nothing to lose. Coming out the jacket cause we're turning up the heat.